negation of an open set. In other words, because if a set's not open, it doesn't necessarily mean it's closed. Okay, even though you kind of even though it's true about doors, it's not true about sets. Okay. Why? Well, let's just see what the definition is. Definition: a set E is closed if E. Okay. Now, the picture of a closed set is something like this. It's some set that contains, in some sense, all its limit points. That's it. So a set E is closed if E contains all its limit points. Okay. Very good. So a closed set kind of looks like something, but the boundary is included in some sense. So let's give an example. In R, let's see if this is true. Is a point closed in the real line? Does it contain all its limit points? What are the limit points of a single point? Nothing. There are no limit points. So it contains all its limit points. Yeah? Good. So in R, a single point, P, is closed. The single point P is closed. Okay. What's another thing that's closed? Well, here's another example of something that's closed. This is the interval AB that includes, first of all, is that set closed? AB? Interval, open interval? No. Why? A and B are limit points. So suppose I throw them in. Is this now closed? The claim is yes. So this is the set of all x such that A is less than or equal to x, less than or equal to B, is closed. And that's why we call it a closed interval. Okay. And I will just mention to you that there are the other intervals, A, B, and A, B, where you include either A or B. Are these open sets? Are these closed sets? They are neither open nor closed. Yes? So to be open is not the opposite of being closed. These are sometimes called half open. That's just the way intervals. But the point is, they aren't open, and they're not closed either. Okay, here's another example. What about in R, also in the real line, is the empty set closed? Yes, why? It contains all of its limit points, which are none. There are no limit points. Excellent. Is the entire real line closed in itself? Does it contain all of its limit points? Clearly, they're both closed. So do you see that it's possible for a set also to be both open and closed? The empty set and the whole real line are both open and they're both closed. We have a special name for that. Sometimes people call them clopen sets. Okay. They're clopen. All right. That's kind of, not too many people use that, but it's one of those words that if you say it, people know what you mean, right? It's very clear. Okay. Excellent. So this suggests something, actually, something rather important. This idea that if you have a set that isn't closed, there is a way to try to close it, right? So, for instance, look at this set B, or running example, set B here. Is this set, let's just take a look at this rectangle here, the mouth. Is this mouth closed? Clearly not. It's smiling at you, right? It's not a closed mouth. Okay. But how could I make it closed without shutting its mouth? Oh, maybe I should give it an upper lip. That's right. Yeah, let's give it an upper lip here. And the claim is that's going to be closed. Now, that might seem obvious, but it may be not as obvious as it looks. But let's make this definition. So, example, the mouth of B is not closed. Is it open, the mouth of B? Not as a set, right? It's not an open set, right? Okay. It's neither open nor closed. Can we close the mouth? Can we close it? Okay, so here's the idea. The idea is, let's look at, the book uses this term, it's not standard, E prime. Let's let E prime be the set of all limit points of E. We'll define the term, this is a standard term, the closure of E is defined, well, first of all, it's notated by a bar. You put a bar over the set, that's the closure. It is the set together with its limit points. E prime is not standard notation, E bar is. E prime is just what the book uses. This is very, very standard notation. Okay, that's the closure. And of course, one of the big questions you have to ask yourself is E bar closed? Now, do you see why it's not obvious that E bar is closed? Why is it not obvious? Jenny? Yeah, the issue here is once you throw in this set, to say that E bar is closed means you want to show that the green plus red contains all its limit points. And so you want to make sure that any point that is a limit point of green plus red, that it's maybe possible, perhaps, that that's a limit point of green plus red, but it's not a limit point of green, right? So so there is something to show here, and we will try to show that next time. What do you think the answer is? Yes, because we're calling it the closure. And we'll prove this next time. Okay. Okay, we'll see you next time. Oh, by the way, just one more comment. The notion of a dense set, your book has a definition, but it's much easier if you know what a closed set is. So a set is dense, a set E is dense in X if E closure is all of X. We'll say more about that next time as well.